Okay, so in this example, we're being asked to compare two different functions, y equals e to the x and y equals ln x. So the key connection here that we're ultimately going to be making is that they are inverses of each other. So I'm going to take some liberties here when graphing these two functions that we wouldn't know if we didn't otherwise know that. But just follow along and this will start to click and make some sense of what we're getting at after you kind of see this. Okay, so they're asking us to graph y equals e to the x and y equals ln x. So if I was to graph y equals e to the x, I'm going to take the standard x values for most tables of values parent functions that we'd use. -2, -1, 0, 1, and 2. Which gives us the values of 0.135. Now if you don't know how to get these, you can get these on your calculator by using the e to the x button on your calculator. It's just that simple. 1.00, 2.718, and 7.390. Okay. So what we're going to do next here is we're going to create a table of values for y equals ln x. Now what I was talking about before was that if we actually take our y values for e to the x and plug them in for our x values, it's going to make this graph look a little bit nicer because they are inverses of each other. So this is where you're going to use that ln button on your calculator. Often on calculators, the ln and the e button are the same button. Just to get one of them, you have to hit the second or shift button on your calculator. So if you go ln of 0.135, you're going to get approximately -2. If you go ln of 0.368, you're going to get approximately -1, etc. So you kind of get the idea there. Okay, so what I'm going to do next is I'm actually going to graph them both. Noting, when I look at my x's here, I need my x's to go basically all the way from -2 to 7, and my y's, I need them to go from -2 to 7. So, actually 7.39. So I'm going to make this nice and just a standard xy axis actually. I'm going to always label your x and your y. I'm constantly saying to students. So 1, 2, 3, 4, 5, 6, 7, -1, -2, -3, -4, -5. It doesn't really matter. We're only going to go to -2 there. And then our y's, we need them to get all the way as low as -2 and as high as 7. So, and I'm just going to label them every second one. And that's fine. Okay. So now we have enough stuff to play with here. Now I'm going to grab a couple of different colored markers to graph this, so my graph looks nice and colorful. So when I plot these points here, I'm going to start with e to the x. Right there. -1, 0.38. It's not perfect. Never is. And you'll notice here that we have an asymptote. We have an asymptote at x equals 0. That's because if you think about it, one way of thinking about y equals e to the x is you can kind of think of it as 2.718 to the x. So it's pretty much just your standard exponential function. It's just it's a little bit it's not a nice whole number basically. Okay, so we got to do our next round here. When x is 0.135, y is -2. And what you'll notice here is that we now have an asymptote at y equals 0. So before I think I said x equals, sorry, now we have an asymptote at x equals 0, before it was at y equals 0. So now let's try to make some connections. between these two graphs. Okay, so I'll just label both these y equals e to the x and y equals ln x. So here's the connections we can kind of make. And they're all just really your standard connections you're going to make with any inverse graph. Y equals e to the x has a horizontal asymptote at y equals 0, and y equals ln x has a vertical asymptote at x equals 0. That's point 1. Point 2 is that the domains become swapped, and so do the ranges. Now, if you're unsure what I mean by that, it's actually quite simple. If we're talking about y equals e to the x, the domain, right, is unrestricted. X can be all real numbers. And the range is y can be anything so long as y is greater than 0. Now, if we're talking about y equals ln x, the domain is x can be anything so long as x is greater than 0, and the range is that y is unrestricted. Y can be all real numbers. So that's what I mean by they're swapped. Looks like swooped. Swapped. Okay. What else can we note here? Any other interesting points? The key idea here is that they are inverses of each other. In other words, they undo each other. So what one does to the other, it undoes it. So like, what I mean by that is if we plug 1 in for e to the x, we get 2.718, and if we plug 2.718 into ln x, it brings us back to 1. Notice how we've kind of gone full circle there. We learned about our inverses in grade 11 functions. I use the analogy of think of it as a machine that undoes what happened. So like if you think about a machine that makes that takes computer chips and plastic and electronics and it converts it into a PlayStation 4, then think of the inverse of that function as one where you put in a fully assembled PlayStation 4 and this robot fully disassembles it into its original form. That's what it means by they undo each other. So hopefully this makes some sense and you can kind of get the connection here. I mean, one of the key ideas here is that if you took the ln of e, you would get 1. So hopefully you guys get the idea. And it's not really a huge thing, it's just kind of just to give you a basic understanding of how e and ln relate. And I mean, really the big thing, I know I've kind of been talking a lot here, but the big key takeaway here is that y equals log base e x. That's the same thing as y equals ln x. So that's why they're inverses, because if you think about this function here, this means that x equals e to the y. Right? The inverse of that is that y equals e to the x. So that's kind of the key takeaway there. I'm not going to leave that on the board just because I don't want that to confuse anyone. But leave the top part up there. So hopefully that makes some sense. Let's move on to the next examples.